Okay, so this picture is just another way of looking at intra versus intermolecular forces. So again, intra is within a particular molecule, and then intermolecular bonds or intermolecular forces are the forces between those molecules. Okay, so the first intermolecular force that we're going to talk about is dipole-dipole forces. So remember we said that any polar covalent molecule, okay, so remember polar covalent was a classification for an intramolecular force. That type of molecule always has a dipole because it has some region of positive charge and some region of negative charge, and that's what a dipole is. So when you have a molecule that itself is polar covalent, that means that the intermolecular force is always going to be dipole-dipole because you have multiple dipoles. So each molecule has a dipole, and so the forces between those molecules is called a dipole-dipole force. So you'll notice down here it says dipole-dipole bonds are approximately 1% the strength of a covalent bond. So you'll remember that covalent bonds were our weakest type of intramolecular force. So this is sort of pointing out that intermolecular forces is always much weaker than any kind of intramolecular force. Okay? So again, if we're thinking about something like hydrogen chloride, so you've got hydrogen bonded to chlorine. Chlorine is more negative, hydrogen is more positive. So then if we have, another molecule that looks that same way, okay, so this is our more positive end, this is our more negative end, there's going to be an attraction between this thing that is negative and then the hydrogen that is positive. And so that's our dipole-dipole force, okay? And they are basically going to arrange themselves in order to maximize the interactions, the positive, negative interactions, the attractions, and minimize their repulsions. Okay, and so that's how all of our molecules will organize relative to one another because that's the most energetically favorable. Okay, so again, this would be our dipole-dipole bond, and then within the molecule itself is our polar covalent bond. Okay, so hydrogen bonds is our strongest type of intermolecular force, okay? In order for something to count as a hydrogen bond, you have to have, obviously, sorry, that got messy, obviously hydrogen, and then in addition to having hydrogen, you have to have nitrogen, oxygen, or fluorine, okay? So hydrogen bonds are just sort of particularly strong class of dipole-dipole force. So the reason that hydrogen bonds are so strong is, one, the bond is extremely polar. So you'll remember that hydrogen is a little bit more positive in terms of its electronegativity. It sits sort of around the area of the transition metals, and then nitrogen, oxygen, and fluorine are up and to the right on the periodic table, which are our most electronegative atoms. Okay, so it's a very polar bond because you have something that is more positive and something that is more negative. In addition to that, because hydrogen is so small, it means that the molecules can get very close to one another. Okay, so their attractions are maximized just because of the size of the hydrogen atom. So if we look at a graph like this, it's at the bottom of the page, this is the boiling point of different molecules. And so if we're talking about boiling point, that's representing a phase change. And so that is a signal to you that you need to be thinking about intermolecular forces. You'll notice that H2O has the highest boiling point of the substances that are listed. That is because it is the only substance listed that has hydrogen bonding. Okay, so the stronger our intermolecular forces. Intermolecular forces are often just abbreviated as IMF, and you can write that when you're doing your free responses for your AP, and that's fine. So the stronger our IMF, that corresponds with a higher boiling point and a higher melting point because it's going to require more energy to break those bonds. Okay, so you need to put in more energy, a higher temperature, and so on. Okay, so then our weakest kind of intermolecular force is London dispersion forces. Okay, so notice these are only 0.01 to 0.1% the strength of a covalent bond. Okay, so much, much, much weaker than even the weakest intramolecular force. Okay. One important thing to keep in mind about London dispersion forces is that all molecules experience some form of London dispersion forces. However, they are really only significant for molecules that are nonpolar or have are nonpolar covalent in terms of their intramolecular forces. Okay, so remember, we've been talking about intermolecular forces for things that have a positive and negative end of the molecule. So what kind of intermolecular forces do molecules have if they don't have that polarity within the molecule themselves? So we can think about something like a hydrogen molecule. So if you have multiple hydrogen molecules that are near one another. Okay, so obviously they have equal electronegativity, so there's no inherent dipole within the molecule. However, by virtue of having electrons, what can happen is that so electrons move around randomly. And what can happen is if the electrons shift to one side of the molecule just by chance, that creates what's called an instantaneous dipole. Okay, so by chance, let's say more of the electrons are shifting to this left side of the molecule. Okay, and so what that does is that it leaves the other hydrogen atom more positive, so it creates a temporary dipole moment. Okay. In turn, what that does is because you've got another hydrogen molecule nearby, if you've got something positive on this end, that means the electrons are going to be attracted to this end of the other hydrogen molecule. And so it's going to induce a dipole in the other hydrogen molecule, okay? And so one induces another and so on, and it creates sort of a domino effect. And again, this is just by virtue of electrons distributing randomly to one side of a molecule, and then the electrons in nearby molecules will shift to maximize the attractions and minimize the repulsions. Okay, so one important thing to keep in mind here is that our London dispersion forces tend to be most significant for molecules that are larger or more massive. Okay, so the larger or more massive our molecule, the stronger our London dispersion forces will be. So something like diamonds that are completely made up of carbon, we know that they're extremely strong, and that's because there are so many carbon atoms that, you know, the London dispersion forces are actually extremely strong. Okay, so this, there's a misspelling here. This both is supposed to say bottom. Okay, so you want to think here about our trends in terms of the size of molecules. Okay, so for example, the halogens all experience London dispersion forces. So again, if we're thinking about our diatomic molecules, but the forces become stronger toward the bottom of the group. So F2 and Cl2 are both found as gases in nature, Br2 is found as a liquid, and then I2 is found as a solid. Okay, so that's in order of decreasing down a group. Okay, so towards the top we have gases in the halogens, and then towards the bottom we have a solid. And that's because as we move down in a group, our atoms tend to be larger, and so that actually makes a difference in what phase we find our substance to be in. Okay, if we're thinking about our intramolecular bonds and what that means for what type of intermolecular forces we can find, so we have intramolecular bonds that can be either polar or ionic or nonpolar. Okay, if our intramolecular bond is nonpolar covalent, then our only option for our intermolecular bond is London dispersion forces. If we have a polar covalent or ionic intramolecular force, then our options for intermolecular bonds are either dipole-dipole or hydrogen bonds. Okay, and again, this represents the strength differences. It's really, really, really important to keep in mind that intramolecular forces are always, always, always significantly stronger than intermolecular forces. Okay, and again, stronger intermolecular forces correspond with higher melting points and boiling points. The weaker our intermolecular forces, the lower our melting points and boiling points. Okay, so let's think about this in-class problem. So we want to arrange these different carbon and hydrogen molecules in order of increasing boiling point and justify your answer. Okay, so take a moment and think about that. Okay, so methane should have the smallest boiling point, and then C2H6, and then C4H10. So this should be our highest boiling point. So these all have London dispersion forces. You could argue that they have dipole-dipole as well, but carbon and hydrogen are actually predominated by London dispersion forces. But either way you think of it, you should realize that C4H10 has the largest molar mass and therefore is going to be more polarizable when we're thinking about London dispersion forces. Okay, so we'll talk about some more examples in class and we can go over these, but think about something like BaCl2, H2CO, HF, and neon. Okay, and take a moment and think about what intermolecular forces or what forces are holding those substances together, and we'll talk about those in class. Okay, so the next thing we're going to discuss is some of the properties of liquids. So one of the things that you need to be familiar with is surface tension. And all surface tension is a measure of the inward pull by particles in the interior. So if you have some liquid particle that is sitting on the surface of whatever liquid you're talking about, it's going to experience intermolecular forces with particles that are to the side of it or below it. Okay, so the more sort of inward pull that particle has, or the more intermolecular forces it has, the greater the surface tension. Okay, so we can think about something like, okay, mercury, okay, actually pulls in on itself quite a lot. Okay, and then water less so, and then alcohol really does not pull in on itself quite as much, and again that has to do with the polarity of the molecules. And this ties into thinking about cohesive versus adhesive forces. So cohesive forces refer to, so co means, you know, something that is like you, so the intermolecular forces within the liquid itself. And then the adhesive forces is the force between the liquid molecules and whatever container it's in. So cohesive versus adhesive forces. And how these two differ from one another, or how they're balanced, is going to have an effect on the way the liquid actually behaves. Okay, and one of those is capillary action. Okay, and capillary action is the rise of liquids up a narrow tube. Okay, and that, you know, that's the way that plants take in water, is through capillary action. So if we're thinking about something like mercury, that has a high degree of cohesive forces. Okay, this was H2O, and this was alcohol. Okay, we can think about water as being kind of in the middle, and then alcohol has a high degree of adhesive forces. Okay, so if we're looking at this image on the bottom, this tube on the left is a test tube of water, and then mercury is on the right. So you'll notice that this meniscus that we say is formed in water, that means that water has slightly higher adhesive forces, so it's attracted to the surface slightly more than mercury. So mercury forms this concave structure, which means that it is sticking to itself more than to the sides of the tube. Okay, so we'll finish up the next several pages in class, so don't worry about those next few pages, and we'll make sure to finish up